Okay, so we're going to do a quick Lecture 7 recap. So Lecture 7, we started talking about chemical kinetics. So we've got our chemical kinetics. And chemical kinetics is basically talks about the reactivity of a reactant or reactants, so how quickly a reaction occurs. So how quickly a reaction occurs due to reactant reactivity. Okay, this is in contrast to chemical thermodynamics, where we're talking about the reaction, our reactant energy versus the product energy. So in reference to each other, how looking at their energies will tell us if a reaction will occur, not how fast it will occur, like our kinetics will. So this talks about the Gibbs free energy. Remember our delta G. And if delta G is negative, we have a spontaneous process, and the reaction will occur without any additional energy. So if we have something that is thermodynamically and kinetically favored, we have a reaction that will occur. These reactions occur due to collisions between molecules. So reactions are a result of effective collisions. So collisions between molecules with the correct orientation and enough energy. So they have to have at least the activation energy, if not more. So to get an effective collision, or to make it more likely to have an effective collision, we can increase concentration, increase temperature, increase surface area, or add a catalyst. These are all ways to increase effective collisions and increase rate. Okay. The rate of a reaction, so let's take some generic reaction. A goes to B. A is our reactant, B is our product. We would say that the rate of this reaction is negative delta A concentration over time. Right? So the change in our concentration over the change in time. So this would be called our relative rate equation. So this would be the rate of disappearance of A. We could also write it in terms of the appearance of B. So delta change in B concentration over change in time. So you're looking at two concentrations at two different times to determine the relative rate. So you'd be given data to put into this to figure that out. This is assuming we have a 1-to-1 mole ratio. If we do not have a 1-to-1 mole ratio, we can relate the rates of appearance and disappearance using additional modifiers. So if we have AA plus BB going to CC plus DD, where all of our lowercase letters are going to be the stoichiometric coefficients, uppercase are our species. So taking into account stoichiometry, we would write our relative rate equations as -1 A delta A delta T equals 1 -1 B over delta B delta T 1 C over delta C delta T 1 D delta D delta T. So if we know the rate of one substance, we can then put it into this equation and find the relative rate of another one. And again, these in this case are reactants. So we look at the rate of disappearance. So these are looking at a space of time, and rates themselves are going to decrease as the reaction goes on because our concentration of reactants decreases. So rate decreases over time. Unless you have a first order process, unless you have a zero order process. So if we think about our rate, so we look at concentration of any reactant, let's just call A, over time, initially the rate is going to be very quick because we have a large concentration of A, but over time that rate will decrease and we get a petering out of that decrease. So over time, rate will go down unless you have a zero order process. So as such, rate is not the same. So rate does not stay consistent. So a lot of times when we're talking about rate, we're talking about an instantaneous rate. So instead of a relative rate, so looking at 2 points and looking at the concentration versus time for those 2 points, we're instead going to look at the instantaneous rate, which is basically the tangent, the slope of the tangent line at any point so if we're talking about a rate, usually it's the instantaneous rate at the beginning of the reaction. So like right here, we'd have a really, really steep rate. But right here, it would kind of peter out a little bit. Here, even more. And then here, so on and so forth. So our instantaneous rate will go down. And then the relative rate, what we were looking at before, we were talking about taking 2 points, such as here and here, and looking at their concentrations and their times. So the instantaneous rate will not be the same as the relative rate. But if a rate is reported, they're usually talking about an instantaneous rate. So our instantaneous rate itself, take the slope, and you take delta y over delta x of that slope line. And that'll give you your instantaneous rate. Okay. Last thing we want to talk about is our general rate law. So the general rate law looks like this. Rate is equal to our rate constant, K, times by substance A to its reactant order, substance B to its reactant order. So K is our rate constant. A and B are reactants. M and N are reactant orders. And then M plus N is our reaction order. And both of these can be 1 or 2, 3, so on and so forth, along with 0. Okay? Where 0, reactant order, that means that the reactant has no reactant concentration, has no effect on rate, and then the greater the number, the more the concentration has an effect on rate. Okay, so that is all of the, it's kind of the summary of lecture 7. So a pretty quick one. I'll also do one for lecture 8 in just a minute.